What's up? I'm Vin, and I'm going to go through this Calculus 1 final review practice test, and I'll leave a link to a copy of this test in the description below. Now let's get started. For question 1, we have the limit as x approaches 3, and we have this rational expression here that we're going to find the limit of. So for questions like this, what I like to do first is I like to factor. Okay, I could try plugging in 3 first, but if these expressions are factorable on top and bottom, I always try to do that first. So on top, we're going to have a difference of 2 squares. So we could factor x squared minus 9 as x plus 3 times x minus 3. And then on bottom here, we have x squared minus 2x minus 3. So we're looking for two numbers that have a sum of negative 2, and the two numbers have to have a product of negative 3, which tells us the factors are going to be x minus 3 and x plus 1, because negative 3 plus 1 gives us negative 2. Negative 3 times positive 1 gives us negative 3. And now these factors just cancel out. And what we have now is the limit as x approaches 3 of x plus 3 over x plus 1. And from here, I'm going to plug in x equals 3. And now I'm going to get 3 plus 3 over 3 plus 1, which gives us 6 over 4. And now maybe one more step here would be to reduce this. If I divide the top and bottom by 2, I get 3 halves. Okay, so this would be our solution to question 1. Now, one thing to point out, these are annoying points to lose, but please don't do something like this. Don't just say, all right, this equals x plus 3 times x minus 3 over this, and then just say that these terms here cancel, and then just say, all right, equals, and then 6 over 4 like this. Because if you stop writing the limit notation, then technically you're losing points for communication and notation, okay? So you have to write the limit notation throughout, unless you do the algebra on the side and you just jump immediately to this step here. But make sure you're writing the limit notation, that you don't just say this equals this and then, simplify from there. That's a common mistake. It's good that you get the limit correct, but your notation also has to be good. Question 2, we're going to find the limit as x approaches 4 of 4 minus x over absolute value 4 minus x. So for this one, the tricky part is the absolute value 4 minus x piece. So let's think about how to deal with this. So what comes to mind here is the equation of a line. So let's think about y equals mx plus b. Okay, m is the slope and b is the y-intercept. And in this case, we would have a slope of negative 1 and we would have a y-intercept of positive 4. Okay, so this would be the linear part on the inside. And what I'm thinking of is I'm thinking of a line with the slope of negative 1 and a y-intercept of 4 is going to look something like this. Okay, it would hit the y-axis at 4, and it would hit the x-axis at 4. So if I'm going to sketch out absolute value 4 minus x, I'm going to write this as negative x plus 4 over here. What this is going to look like, so I'm just going to sketch over here, we're going to have basically almost the same line as this, except when we hit the x-axis, the absolute value, instead of going through like this, is going to reflect the negative stuff over like this. Okay, so this is just a rough sketch here of the graph of negative x plus 4 inside the absolute value. And the turning point is at 4. So when we have to find this limit, we're going to have to investigate the left and right side limit at 4. So let's say over here, this line that I'm highlighting in purple, this would be the line y equals negative x plus 4. But then for this line over here, so let's change colors and look at this line over here. This line would have a different equation. This would be y equals, and I just changed the sign of both of these. I would have x minus 4. So now this is going to help us evaluate the limit. We have the limit as x approaches 4 on the left side. When we are approaching 4 from the left, we're on this line in purple. So the absolute value piece on bottom, we could actually replace with negative x plus 4. And now the expression on top, just know that 4 minus x, this is the same thing as negative x plus 4. So we could just write negative x plus 4 on top, like this. What we're basically doing here is we are just using the fact that absolute value negative x plus 4 is a piecewise function, okay? So since we are approaching 4 from the left side for the first limit, we're going with the first piece of the piecewise function, the negative x plus 4 piece, okay? But I'm not going to actually write out the entire piecewise function for this. I could just go ahead and make this substitution. And now notice that these factors on top and bottom match exactly, and they cancel out, and they equal 1. So this gives us our left side limit at 4. And next, we're going to find the limit as x approaches 4 on the right side of our function. And we're going to have the 4 minus x on top, which I'll write as negative x plus 4, But now when we approach from the right side, we're going to be dealing with this equation here. And I'll write the expression over here, x minus 4. Okay, so this is for the next limit. And now we have the limit as x approaches 4 on the right side. And I'm going to factor out a negative 1 on top. And we're going to have x minus 4 and now over x minus 4. So these factors cancel, but we're left with a negative 1 instead. But now what conclusion can we draw here? Notice the left and right side limits are not equal. Okay, so I'm going to make that statement. I'm going to say the limit as x approaches 4 on the left of 4 minus x over absolute value 4 minus x. So this is not equal to the limit as x approaches 4 on the right of 4 minus x over absolute value 4 minus x. So what does this imply? This implies that the limit as x approaches 4 of 4 minus x over absolute value 4 minus x does not exist. Okay, so we're just going to say DNE here. The limit does not exist. Now, if this were a multiple choice question, there is a much faster way to do this. What you could do if this were multiple choice is you could just plug in numbers. So let's say I do a left side limit. If I approach 4 from the left, I could plug in something like x equals 3.9. And notice I get 4 minus 3.9 divided by absolute value of 4 minus 3.9. And this gives me 0.1 over 0.1, which is going to give me 1. And if I find the other side limit here, let's say I find the right side limit. So we'll put this idea over here. For the right side limit, I would plug in something a little bit bigger than 4, like let's say x equals 4.1. And if I plug in 4.1, we'd have 4 minus 4.1 over, and then absolute value of 4 minus 4.1 would go on bottom. And then I'll write this over here. This equals negative 0.1 divided by, we would have positive 0.1 on bottom because we're taking the absolute value of negative 0.1. And then negative 0.1 divided by 0.1 is equal to negative 1. And notice how we get left and right side limits do not match. Okay, so that would be just by numerical approach answering this question. But if we have to show all of our work, this would be the algebraic approach to show that the limit does not exist. Question 3, we're going to find the limit as x approaches infinity. And we have this rational expression here. So just know when you have limits at infinity, okay, so when you see that the limit as x approaches infinity, this tells you to focus on the leading terms. Okay, there's more than one way to do this question, but if you focus on the leading terms, that makes the question way easier. Okay, so I could rewrite this as the limit as x approaches infinity, and now the leading terms here are negative x to the fourth and negative 4x to the fourth. Don't get confused with leading terms being the first terms here. That's not the case. The leading terms are always the highest powers of x, and their coefficients go along. Okay, so we have negative x to the 4 over negative 4x to the 4. And now from here, just imagine there's a negative 1 in front. X to the fourth over x to the fourth cancels, and we get negative 1 over negative 4, and this is equal to positive 1 over 4. Okay, so this is our limit for question 3. Question 4, we're finding the limit as x approaches minus infinity, and we have square root of x squared plus 9 over 2x minus 5. So students, for questions like this, will look at the minus infinity and say, oh, let me focus on the leading terms. And then they say the limit as x approaches minus infinity, they do the square root of x squared is x, and then they have the leading term 2x on bottom. They cancel, and they say the limit is equal to 1/2. But don't do this. This is a very dangerous bear trap. The reason why this is no good is because the limit is going to minus infinity, not positive infinity. So what we have to think about here is the square root of x squared is not x. It's equal to absolute value x. So that means the square root of x squared is a piecewise function. And I could express this piecewise function here as x if x is greater than or equal to 0, and it's equal to minus x if x is less than 0. Okay, so this is just how we define absolute value x as a piecewise function. If I were to sketch it out over here, we would have the v shape here for absolute value x. But what this actually means, if we connect this to the piecewise function, is that when we're on the positive side of the x-axis over here, we're dealing with the line y equals x. And when we're on the negative side, we're dealing with the line y equals negative x. Okay, so in this question, since we're going to minus infinity, we're going to be on this side of the absolute value function. So now what I could do is I can focus on just the leading terms here. I can say that this is the limit as x approaches minus infinity of just square root x squared over 2x on bottom. But now when I take the square root of x squared, remember, the square root of x squared is not equal to x, it's equal to absolute value x. And we're dividing by 2x, but since we are going to minus infinity, we're going to replace the absolute value x on top with minus x instead of x. Okay, so the algebra we're doing is we're replacing this with minus x over 2x. So now when the x's cancel, we're actually going to have a limit of -half instead. So this is our answer to 4. Question 5 is g of x continuous at x equals 0, and we have to explain using the limit definition of continuity. So for this one, we have to know that if the limit as x approaches c of f of x is equal to f of c, then we could say that f of x is continuous at x equals c. Okay, so this is a good definition to know for a calc final. Okay, so this is something that we just have to be able to use. So what that tells us for a question like this is that first we should find the limit as x approaches, in this case, 0 of g of x, okay? Because the c value is where you're trying to see if the function is continuous. So here we want to see if g of x is continuous at 0. So let's start that process. And since our function is piecewise here, we're going to have to take the limits from the left and right side of 0. So we're going to have first the limit as, let's say, x approaches 0 on the left, we'll do first, of g of x is going to be equal to the limit as x approaches 0 of, on the left side of, we're going to replace g of x with the sine x over x piece. The reason why we're going with that piece, the way I think about these, is when we're looking at 0 on the number line. So let's just imagine 0 here. If we're approaching 0 on the left side, that means we're on the less than 0 side, okay? So this is the x less than 0 side when we're approaching 0 from the left. So that's why I'm replacing the function with the sine x over x piece. And then this is a classic limit. The limit as x approaches 0 of sine x over x is 1. So when I approach from the left and right side, I'm also going to get a limit of 1 if I'm focusing just on sine x over x. So next we'll find the limit as x approaches 0 on the right side. Okay, so now we're going to come in from the right side. So this is the greater than 0 side. So we're going to replace g of x with this piece. So we'll say the limit as x approaches 0 on the right side of g of x is equal to, we have the limit as x approaches 0 on the right of e to the x minus 1 over x. And for this part here, we are going to use L'Hopital's rule, because if I plug in 0 for x, I'm going to get e to the 0 minus 1 is 0, because e to the 0 is 1, and then I divide by 0. And 0 over 0 is an indeterminate form for limits, okay? So 0 over 0 means this is an indeterminate form. A common mistake that students make is they get 0 over 0 and they're just like, oh, the limit doesn't exist. But that just means you have more work to do. So a nice thing we could do here is just apply L'Hopital's rule. So I'm just going to say here that this limit is equal to the limit as x approaches 0 on the right side of, we derive the top, the derivative of e to the x is e to the x. The derivative of minus 1 is 0. And then we divide by the derivative of the bottom is 1. Okay, so we're just applying L'Hopital's rule. And now when we simplify this limit, this is going to equal, we're going to have e to the 0 divided by 1 is equal to 1. So notice what this tells us. This tells us, since the left and right side limits are equal to 1, the limit in general of g of x at 0 is equal to 1. Okay, so I'm just going to summarize here. We have the limit as x approaches 0 on the left of g of x equaled the limit as x approaches 0 on the right of g of x was equal to 1. So this implies that the limit as x approaches 0 of g of x is equal to 1. Okay, so this establishes our limit. For some classes, like let's say this were AP Calculus, or some universities might require you to say a little bit more before you apply L'Hopital's rule. A common mistake, don't say like at this step, like, oh, equals 0 over 0. The moment you say the limit equals 0 over 0, that's a notation mistake, and you're going to lose points for that. The correct way to say indeterminate, if you have to justify why you're using L'Hopital's rule, is you would say the limit as, in this case, x approaches 0 on the right of the numerator part is e to the x minus 1 is equal to the limit as x approaches 0 on the right of the denominator part is x, and that they both equal 0. And then you would say, therefore, 3 dots means therefore L'Hopital applies. Okay, so this would be justification for why we could use L'Hopital, but a lot of universities are okay with you just like jumping into L'Hopital's rule. But once again, know your standards, like how much does your professor or your teacher want you to show. This is usually more than enough for universities. So now that we have the limit is established, okay, we established that the limit exists. The next thing we should check here is what is the function value for g at 0. And notice this is a piecewise function. G of 0 is defined right in the middle is equal to 1. Okay, so now notice we have the limit as x approaches 0 of g of x is equal to 1. The function value at 0 is equal to 1. Now all we have to do is just summarize all this. We're just going to tie it all together. We're going to say that the limit as x approaches 0 of g of x is equal to g of 0. They both equal 1. So this means, so we could say from here that, well, now we could say therefore, let's just make this a little neater. Therefore, g of x is continuous at x equals 0. Okay, so this here would get us full credit for a question where we're required to explain using the limit definition of continuity. Okay, we say the limit as x approaches 0 of g of x equals g of 0 equals 1, and this tells us g is continuous at x equals 0. Question 6, we're going to use the intermediate value theorem to explain why h of x has a root on the interval here from 2 to 3. So the concept of IVT, this is what I like to say to help students understand IVT, is I tell them in 1999, I was 5 feet tall. And this is true. I was 5 feet tall in 1999. That was 5th grade. Okay, so I was 5 feet tall. And today, so at the time I'm making this video, this is 2025, I am now 6 feet tall. And the question is it possible that I skipped 5'4"? And most students, when they hear that, they're like, no way, because 5'4" is between 5 feet and 6 feet, and you have to hit every height in between. So that is basically all the intermediate value theorem is saying. That as long as your function is continuous, as long as you grow continuously with your function, you have to reach every value, every y value between these two y values here. So if I'm going from y equals 5 to y equals 6, I have to reach every single real number between 5 and 6 on my way from here to here, as long as I'm dealing with something continuous. But notice h of x is a polynomial. So I'm going to say that h of x is a polynomial, and therefore h of x is continuous. Okay, that's something you're just allowed to say. All right, you don't have to show the proof of this. You could just say, since h of x is a polynomial function, h of x is continuous. In AP Calculus, they'll say things like h of x is differentiable, and if h of x is differentiable, that implies that h of x is also continuous. So now the other work we have to show here is what's going on at the endpoints. So the endpoints here, like these values here, like the 2, 3, this represents, let's say, the year 1999, and this represents the year 2025. So all I do now is I just plug in h of 2 is equal to, we have 2 to the 3rd power minus 4 times 2 and then minus 3. So this gives us 8 minus 8 minus 3, which is equal to negative 3. And now I could plug in the other endpoint. I'm going to say, and we have h of 3 is equal to, we have 3 to the 3rd minus, and we'll just make that neater. So we have 3 to the 3rd power minus 4 times 3 minus 3. And this is going to simplify to, we have, I'll just do this over here. We have 27 minus 12 giving us 15. And then 15 minus 3 is going to give us 12. Okay, so the function value at 3 is equal to 12. But now let's think about what does it mean for a function to have a root? Okay, so a root is a value of a function where the function is equal to 0. Okay, so what I'm imagining for that part is we have our function h of x. We just showed that h of 2 is equal to negative 3. So that would be way down here at negative 3. And then we have h of 3. So we go 1 over. Now we're way up here at 12. Okay, so how do we know the function is going to have a root? Well, no matter how we connect this here, if we have to draw this continuously without lifting our pen off the paper, at some point we're going to have to pass through the x-axis, and this would represent our root. But now we just have to communicate all of this using the language of the theorem. So we just have to comment, since the root value here is 0, but since 0 is between negative 3 and positive 12, notice these are the two function values here. So since 0 is between negative 3 and 12, and we already said that h of x is continuous, by IVT, I'll abbreviate the intermediate value theorem, by the intermediate value theorem, there exists, I could write a backwards capital E. I promise that that means there exists. There exists a value, let's say c, where c is between 2 and 3, such that, and then I write my conclusion here, that h of c is equal to 0. They're not actually telling us to find the value c. They're just asking us to explain why that the function has a root. Okay, so this is how we would write our response here for full credit. We just mentioned that the root is between the function values here. It's between -3 and 12. So by IVT, at some point in time, the function is going to reach a height of 0. Question 7, we have the graph of y equals f of x and its asymptotes, and they're shown below here. And we're going to find these limits over here. So first, we want to find the limit as x approaches -3 on the left side. And notice that we have a vertical asymptote over here at x equals -3. Okay, so x equals -3 is a vertical asymptote. So I'll just move this over here so it doesn't block the graph. And what we have is, if we're finding the limit as x approaches -3 on the left side, that means if we look over here, see how -3 is over here, that if we approach on the left side, we're going to be following the graph like this. Okay, so as we approach -3 from the left, notice the y values of the graph are dropping this way. So this tells us the limit as x approaches -3 on the left side is approaching -infinity. Okay, so that is how the graph is behaving. And now if we look at the next limit, the limit as x approaches -3 on the right side, that means we're going to be approaching -3 this way. So we're going to be following the graph up like this. And notice the graph is going up to +infinity. So now what is the limit as x approaches -3 in general? Well, since the left and right limits do not match, we just say that the limit does not exist. Okay, technically the limit doesn't exist because the graph is going up to infinity on the right and to -infinity on the left. But for these questions, we're just going to say more precisely where is the function going at the vertical asymptote on the left and right side. If we had to classify what type of discontinuity this is, we would call this an infinite discontinuity. Okay, so this one over here is an infinite discontinuity. Okay, but we don't actually have to name them here, but I just want to mention that just in case that's vocabulary that shows up on your test. Okay, so we have an infinite discontinuity at x equals -3. So next we're focusing on over here, the limit as x approaches 2 of f of x. So for this one, we actually have to find the left and right side limits ourselves. So notice here, as x approaches 2 on the left side for f of x, we are heading up to a height of y equals 1. Okay, and if I focus over here on the right side limit, as x approaches 2 on the right side, notice that we're heading to the x-axis, so the limit is equal to 0. So here, the left and right side limits do not match, which means the limit, once again, does not exist. And now for the next piece, we're finding the limit as x approaches 3 on the left side. So that means we're going to be looking over here as we approach 3. So here's 3 over here. I'll just make this a little bit bigger. So here's 3. As we approach 3 from the left, notice we're heading to a y value down here. We have a y value here of -1. So our limit as x approaches 3 from the left is equal to -1. And then if we take the right side limit, so now I'm going to go the limit as x approaches 3 on the right side, notice we're heading to the same exact location here. We're heading to a y value of -1. Okay, so when you're finding limits on a graph, you're really just focusing on the y values. And then this tells us, since the left and right side limits at 3 match, the limit as x approaches 3 of f of x is equal to -1. And now finally, we're going to look for the limit as x approaches infinity of our function. But notice that we have a horizontal asymptote. So the graph, we were told, has asymptotes, and you see the dotted line here on the x-axis. This tells us that we have a horizontal asymptote at y equals 0. And this tells us then that the limit as x approaches infinity, if we just follow the graph here to infinity like this, you could see that it's getting closer and closer and closer to the x-axis. So this tells us then that our limit as x approaches infinity is equal to 0. Question 8, we have f of x equals square root x, and we're going to use the limit definition of the derivative to find f prime of x. So we have to know that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so here, this is more of an algebra challenge. So we just have to be able to find f of x plus h, plug in, and do the algebra to simplify. So f of x plus h is equal to square root of x plus h. Notice that I'm just replacing the x's with x plus h. So now I could plug into the limit formula here. So we have f prime of x is equal to, we have the limit as h approaches 0, and now we have the square root of x plus h minus f of x is equal to square root x, and we're dividing this all by h. So now from here, to simplify this limit, we can't just plug in h equals 0 because we get square root x minus square root x is 0 divided by h equals 0, and we get an indeterminate form here. So we actually have to do a little bit of algebra. We're going to multiply the top and bottom here by the conjugate of this expression. So we're going to have the square root of x plus h plus square root x. That's what we're going to multiply the top and bottom by. So we're going to do this, and we're multiplying the top and bottom by that same expression. So now we'll write the result over here. So next, we'll say that this over here, so I'm going to say that f prime is equal to, we have the limit as h approaches 0. And now when we multiply this stuff out, notice that we're doing square root of x plus h times square root of x plus h is just x plus h. Okay, the idea I'm using from here is actually when I multiply a plus b times a minus b, anytime I multiply a binomial and its conjugate, I get the first term squared minus the second term squared. Okay, so I'm doing square root of x plus h times itself is just x plus h. And then the shortcut here is I just do the last term squared is x, and that's what's being subtracted at the end. I get minus x. Okay, if I show all of the gritty details, then technically what I'm doing is I have radical x times radical x plus h, but then I have minus radical x times radical x plus h. And you see how these terms just cancel out like this? So for that part, I could just skip that algebra. I'll just write out the first term squared minus the second term squared. Okay, so these little algebra tricks are really helpful to know for calculus. Okay, the calculus that we're doing here is very algebra heavy. So we'll just make sure that we have these algebra rules down. So now we'll write the rest of the expression. We have h times, and we have square root of x plus h, and then plus square root of x on bottom. And now notice that x minus x cancels out. And we have next, I'll write it over here, we have f prime of x is equal to the limit as h approaches 0, and we're left with h over h times square root of x plus h plus square root of x. And now h over h cancels, and we're left with the 1 on top. So now let's think about what we have left. We have f prime of x equals the limit as h approaches 0 of 1 over, and we have radical x plus h plus radical x. And now we could plug in h equals 0. We get f prime of x now equals 1 over square root of x plus 0. And then also in the denominator, we have plus another square root x. But this gives us 1 over square root x plus square root x is 2 square root x. For question 9, we're going to calculate this derivative here. And for this one, we have to know a few rules. We have to know the quotient rule. When we have u over v prime, this is equal to vu prime, and then minus uv prime over v squared. And we also have to know the chain rule. Okay, so the chain rule is when we have f of g of x, when we have a composition of two functions, and we derive it, we get f prime g of x times g prime of x. It does help sometimes to know the chain rule variance. Like I could say something like this: when I derive tangent inverse of a function, I get 1 over 1 plus the function f of x squared, and then I multiply by the derivative of f of x, so I get f prime of x on top. Okay, so if you want to know these chain rule variants, you can, but for this question, you just have to be really strong with the chain rule, and you also have to know how to do the quotient rule. So let's go ahead and find this derivative now. So we're going to say that when we derive both sides, so I'm deriving the left and right side, that we're going to have dy dx equals, and in this case here, what I'm thinking of in terms of this formula, I'm thinking that f of x, my inside function, is 1 plus x over 1 minus x. So when I use this formula, what I'm going to be doing is I'm going to have 1 over 1 plus the inside function squared. So I have 1 plus x over 1 minus x squared. But then I'm multiplying by the derivative of the inside function. So I'm going to be multiplying by the derivative of, and we have the inside function was 1 plus x over 1 minus x like this. So now for the next step, we're going to derive this part. And I like to call this using training wheels. What you could do is you could say u is the top part here. That's the 1 plus x. And then you could say v equals the bottom part is 1 minus x. And then you find u prime is the derivative of 1 plus x, which is 1. And then we have v prime, the derivative of 1 minus x, is negative 1. And I apply the quotient rule to derive this piece here. Okay, so now for our next part of the derivative, we're going to have dy dx is equal to, we have 1 over 1 plus, this part here I could call 1 plus x squared over 1 minus x squared. Okay, so I'm just going to rewrite this as two separate squares. And now I have times, and I apply the quotient rule. So I have vu prime, so I'm doing 1 times 1 minus x is 1 minus x. And then I have minus u times v prime, I'm doing 1 plus x times negative 1. So I have, I'll say here, negative 1 times 1 plus x. And this is all being divided by v squared. And v is equal to 1 minus x. So I have 1 minus x squared going here like this. So now we could work through some of the algebra. So what we're going to do is we're going to distribute 1 minus x squared to this piece and to this piece. And what we're going to have next on bottom, our derivative, we have 1 minus x squared times 1 is 1 minus x squared. And then we're going to have plus, we have 1 plus x squared like this on top times the 1 minus x squared. But this was all over 1 minus x squared. Okay, so these terms are just going to wipe out nicely. And then on top, we're going to have 1 times this whole expression here. So we have 1 minus x, and then we have minus 1 changes to plus 1. So I have plus 1 times 1 plus x makes 1 plus x like this. And notice minus x plus x cancels out. So I could say in my next line here, dy dx is equal to, we have 1 plus 1 is 2, over, on bottom we have 1 minus x squared, plus we're left with 1 plus x squared. So now for this, we could expand the stuff on bottom, and let's see what we get. So we have 1 minus x times 1 minus x. Don't say 1 plus x squared. Okay, we got to do 1, and if I write this off to the side here, just so you can see the idea, we're doing 1 times 1 is 1, but then we have 1 times minus x and negative x times 1. So we get minus x is minus 2x. And then we get plus x squared at the end. And then when we expand the other piece, we're going to get 1 plus, we get plus x is 2x, and then plus x squared. And notice what happens here. Minus 2x plus 2x cancels out, and we get 2 over 1 plus 1 is 2, and we get x squared plus x squared is 2x squared. So now I could just divide the top and bottom by 2 or multiply the top and bottom by a half. And this tells us our final answer here, the derivative dy dx is equal to, we have 2 times a half is 1 over, if I do a half times 2, I get 1 plus half of 2x squared is just 1x squared. So here is our derivative for this question here. Question 10, we have f of x here, and we want to find f prime of x. So for this question, it helps to know some more chain rule variants. When you derive a function like, let's say, a, and since f of x is taken, I'll use g of x. So let's say I have a to the g of x power. This is equal to g prime of x times a to the g of x. So I have the original exponential function here going after it, but then I also multiply by natural log a. And we could use this as long as we have some exponent here where we have a is greater than 0. Okay, so this is just something that we could use. And for the next piece here, the natural log piece, we could say the derivative of, let's say, natural log, since g is taken, I'll use h of x, would be equal to, I would have 1 over h of x, and then times h prime of x goes on top. So if I apply these two formulas, then I could answer this question right away. I could say that f prime of x equals, I do the derivative of the exponent x squared is 2x, I'm just using the power rule here, times the original function is 2 to the x squared, and then I have natural log of the base is 2. And then for the next piece, I have 1 over the inside. So 1 over the inside function here is x to the third. And then I multiply by the derivative of x to the third is 3x squared. And if I simplify this, I will have my answer right away. Okay, so this is 2x times 2 to the x squared, natural log 2. And then plus x squared over x to the third simplifies to x. So I have plus 3 over x at the end. Okay, so here is our solution to 10. Now, let's say you're looking at these two formulas and you're like, whoa, I don't know if I could remember this. This one is probably more common to show up than the other one. So if you are going to remember one of them, I would remember this one before I remember this one. But then you might be thinking like, okay, how do I derive something like this if I don't have the formula? Well, I would go on a side quest. Okay, and if we look over here, on our side quest. Let's say I just look at y equals 2 to the x squared. So then what I do is I take the natural log of both sides. So I'll write that over here. I'm going to say natural log y equals natural log of 2 to the x squared power. But then you could use the power property of logs and bring that power in front of the log. So we could say natural log y is equal to x squared times natural log 2. Okay, I could bring that power in front. And now I'm going to derive with respect to x. And from here, the derivative of natural log y, I'm using this idea, is going to give us, I'll write it over here in a different color. We're going to have 1 over y times the derivative of y is dy dx. Okay, so I'm using the chain rule here. And that's going to give us this expression over here. Okay, the idea behind this is when I derive something like natural log y, what I'm really doing is using the chain rule. I'm going to say that d over dx is equal to d over dy, then times dy dx. Okay, so this is an implicit differentiation concept. So I'm doing the derivative with respect to y of natural log y, and then I multiply by dy dx. Okay, and that's why I'm getting 1 over y dy dx. And now this is equal to the derivative with respect to x of x squared is 2x, and natural log 2 is a constant, so that doesn't tag along like in terms of having to do more derivatives. Okay, this is another small formula I'll just write over here that shows up a lot in calculus. When you derive something like a constant times f of x, this just works out to the constant times f prime of x. Okay, so I'll just write this part in a different color. So it's c times f prime of x. So over here, natural log 2 is acting like our constant value. So that's why when I derived from here to here, we just have natural log 2 times the derivative of x squared is 2x. And now to solve for dy dx, I would just multiply both sides by y. And notice that I would have dy dx equals, and I have 2x, and then I'll write y next. Y originally was equal to 2 to the x squared, and then natural log 2 just follows after this. Okay, so that's why, see how this derivative matches this part here. If you forget that formula up top, you could just use algebra plus implicit differentiation to get to the same answer. And there's a fun little side quest for this piece. The derivative of natural log of x to the third, there's another fun way to do this. I could just bring that 3 in front first. I could do algebra first and say the derivative of, and then I have 3 times ln x. And then this is the same concept as the derivative of a constant times a function. I leave the 3 alone, and the derivative of ln x is 1 over x. So I still get the 3 over x at the end. Okay, but f prime of x, this is our solution here. Question 11, we have a curve whose equation is given here, and we're going to use implicit differentiation to calculate dy dx. So for this question, I included a graph of the curve to help us see the concept. And we're going with implicit differentiation. And just know the time to use this is when you have an equation like this and you cannot solve for y. Okay, you could try to do a whole bunch of algebra here, but separating y is not going to be nice. And we could see on this graph here that this graph does not represent a function of x because it would fail the vertical line test. So we'll just start taking the derivative as is. We're going to take the derivative with respect to x of y squared minus 2xy plus x to the third equals 4. And one of the real big ideas behind this question is we have to use the chain rule. So anytime we encounter something that's not x, something like y, and the constant at the end is not going to be a problem because the derivative of 4 is 0. But any variable that's not x, we have to use the chain rule. So we're going to try to take the derivative with respect to x, but what we have to do for something like y squared is we have to take the derivative with respect to y and then multiply by dy dx. You could see the dy over dy canceling and bringing you right back to d over dx like this. Okay, but this is the chain rule where we're using the chain rule as an operation. Okay, we're taking the derivative with respect to x. We're going to do this instead. So let's apply that here. We're going to take the derivative of y squared with respect to y, and we get 2y, but then we have to multiply by dy dx. Okay, and now for the next piece, we have this minus 2xy. We're going to have to use the product rule. So for this, I'm just going to put a section over here and say u is equal to negative 2x. So that's the first part of our product. And the second part of our product is y. So when we derive negative 2x, this is not a problem. This is just going to give us negative 2 because we're deriving everything with respect to x. But when we derive y, don't just say 1. The derivative of y is 1 and then dy dx because we are deriving with respect to x. So now we could apply that product rule. Okay, so we're going to go ahead now and just work this out. So the product rule, I'll just write it up here. When you have uv prime, that's going to give you u prime v and then plus uv prime. Okay, so we're applying the product rule here, and let's see what we get. So we're going to have u prime v giving us negative 2y, because I'm doing negative 2 times y. And then I'm going to have negative 2x times dy dx is minus 2x dy dx. And then after this, we have the derivative of x to the third is 3x squared. So we're just going to write plus 3x squared. And now I could set all of this equal to 0. So I'm just going to move this out of the way now. We have this is all equal to the derivative of 4 is 0. And I'll just section this off one more time. So this space over here was our work to apply the product rule. So one idea though I want to explore is I just want to talk about the most common mistake I see with that middle piece is students say, all right, I'm just going to derive this without writing this out. And what they do is they say the derivative of negative 2x is negative 2 times y. And then they write plus 2x dy dx. But just be careful here. This is a very dangerous bear trap. You have to see that negative 2 as distributing through and making both of these parts here negative. But I see that mistake all the time. So I just wanted to mention, for you to be careful of that because, once again, I just see that all the time. Okay. Oh, and I'll also draw here. We did u times v prime. So negative 2x times dy dx. So then what we're going to do is we're going to solve for dy dx. So we need to get these terms here together and move everything else away. So I'm going to go plus 2y on both sides. And I'm also going to go minus 3x squared on both sides. Okay, so we're going to just move all the stuff over. And now what we have on this side, negative 2y plus 2y cancels. And we also have 3x squared minus 3x squared cancels. And now we have in our next line 2y dy dx. And then we have minus 2x dy dx. And now this is all equal to, we have 2y minus 3x squared. And then from here we could just factor out the common dy dx. So we're going to take out dy dx and then write the leftovers. We're going to have 2y minus 2x left in the parentheses here equals, and then we have 2y minus 3x squared. And now from here, we just divide both sides by 2y minus 2x. And then we will have solved for dy dx. Okay, so we have 2y minus 2x going here like this. All right, so these terms cancel. And now we could say our derivative dy dx equals 2y minus 3x squared over 2y minus 2x. But now, just in case this is fuzzy, like what does this stuff actually mean? Well, let's say I look at a point on the curve over here. Let's say the point 2, 2. You could see this point is on the curve, and at this location, we actually have a vertical tangent line. Okay, but then think about what does a vertical tangent line mean? This means the slope here is undefined. Okay, and if you're not sure about that, just know when you have a positive slope, your line goes up. You have a negative slope, your line goes down. A vertical line, your slope is undefined. And when you have a horizontal line, you have a zero slope. Okay, and if you draw this person out, it makes slope guy. If slope guy gives one of you a nightmare, then slope guy did his job. No, this is just really helpful to remember what the slopes actually mean. But we could see here that if I were to plug in, let's say 2, 2 into our derivative here, so I'm just going to think about that. What does that mean if I plug in 2, 2? Well, what I would have is I would have 2 times 2 minus 3 times 2 squared divided by, and then on bottom, if I do 2 times 2, I get 4, minus 2 times 2, I get 4. And you see I have division by 0. And when you have division by 0, your expression is undefined. And if it's your derivative dy dx that has division by 0 and your numerator is non-zero, you're going to have a vertical tangent line like this. Okay, so this is just supporting what is going on the graph here. So our answer checks out. Question 12, we have w of x, and we're going to find a few things. The intervals where w of x is increasing, decreasing. The local extrema of w of x, the intervals where w is concave up, concave down, and the point or points of inflection. So for this one, let's just go ahead and start taking derivatives. So we have w prime equals, and same idea as before, the chain rule variant for e to the x. And this is when we have something like e to a constant times x is e to the constant times x, and then the constant goes in front like this. So now I'm going to use the product rule, which is when we have uv prime, this is u prime v plus uv prime. And if I define terms here, I'm going to say u1 because we're going to be doing two derivatives, so we'll have to do product rule twice. So u sub 1 is x, and then v sub 1 is going to be e to the 2x. So u sub 1 prime is 1, that's the derivative of x. V sub 1 prime, we're going to use this chain rule variant here, is e to the 2x, but then the coefficient of x is 2, that just goes in front like this. Or I could say the derivative of 2x is 2, but either way here we are using the chain rule. So now let's just go ahead and use that product rule. So we have u prime times v is 1 times e to the 2x, and then plus we have u times v prime is going to give us x times 2 is 2x, e to the 2x. And now I wrote it like this so that we could see that when we factor, so we're going to factor out an e to the 2x here like this, we are going to be left with, let's see in the next line, we have w prime equals e to the 2x times 1 plus 2x. Okay, so here is our first derivative. I could start finding the intervals where w is increasing, decreasing in the local extrema from here, but let's get all of our derivatives in a row first. So next what we'll do is we'll define u sub 2. So our next u term is going to be, we could say here, 1 plus 2x. And I know that before we put the first term as our u like this, we said u equals x, but I'm just going to keep it consistent. If I made the polynomial part the u term, I'm going to do the same thing here. But it doesn't matter if I make u equal to e to the 2x. And then I'll have u sub 2 prime is equal to 2. That's the derivative of 1 plus 2x. And then next we have v sub 2. The next part of our product is e to the 2x. Okay, so remember, the product rule, the u and v terms are interchangeable because multiplication is commutative. With the quotient rule, though, we have to be very, very, very careful with the order. We can't just mix and match stuff. So now we have v sub 2 prime is equal to 2e to the 2x all over again. So now I'm going to say next, w double prime of x equals, and now let's just go ahead and apply this product rule. Okay, so we're going to have u prime v. So I'm doing 2 times e to the 2x is 2e to the 2x. And then we have plus, I'm going to do u v prime is 1 plus 2x times 2e to the 2x. And now this time I could factor out a 2e to the 2x. And I'm just going to put a times 1 in front of all of this. Okay, so a times 1 here. And now if we focus, see how for this next part here, we have a 2e to the 2x in common. So we factor that out, and this tells us w double prime of x is equal to 2e to the 2x times, we have 1 left, plus 1 plus 2x. And now we simplify this, we're going to have w double prime of x equals 2e to the 2x, and then we have 1 plus 1 is 2, so we have 2 plus 2x. Okay, and if I want to factor out another factor of 2, I could bring a 2 out, and that'll bump this up to a 4, e to the 2x, and then I divide everything by 2, and I get 1 plus x on the inside. So now we're ready to find all the values we need. So for the first two parts here, this is going to be based off the sign chart for w prime of x. And for the second part, this information is going to be based off what we find from the sign chart of w double prime. So let's go ahead and make a sign chart for w prime. So I could say w prime of x equals 0, and this is going to be true when 1 plus 2x equals 0. Remember what I said before, that e to the 2x is an exponential function is always positive. So I'm not going to be able to get any roots out of this. And this is going to tell us here that x equals negative 1/2 is a critical point. And then what we could do with this information is we can make a sign chart for w prime, and we could say we have a critical point at negative 1/2. If I were to plug in something like, let's say 0, so something like 0, w prime of 0, if I plug in, would give us e to the 0 times 1 plus 2 times 0. This would give us 1 times 1 is 1, which is greater than 0. And notice that x equals 0 is to the right here, and that made our derivative positive. I could put a plus sign here for our sign chart for w prime. If I plug in something like, let's say, negative 1, this would give us, we would have e to the negative second times, and then we have 1 minus 2. But this is going to give us something, I want to actually find the value here. We're going to have a positive times a negative, and this will change to negative here. So we have a sign change. If we talk about the behavior of our function w, our function w is decreasing and then increasing. Okay, so we have a local minimum at x equals negative 1/2. If we want, what we could do all at once is we can make our sign chart for W double prime right under it. For W double prime here, notice that we're going to have W double prime is equal to 0, and this is true when 1 plus x equals 0, which tells us we have a root here of x equals -1. Okay, so for this sign chart, we're going to be seeing what's going on the left and right side of -1. So we investigate, we're going to have W double prime of, let's say I plug in 0 again here. We're going to plug into our second derivative. That's going to give us 4e to the 0 times 1 plus 0, and this is something positive. Okay, so we have a plus here. And then next, if I plug in something like, let's say, -2, something to the left, I'd have 4e to the 2 times -2 is -4. And then I have 1 minus 2. This is going to give me something negative. Okay, so I'm going to have a minus here. And this is going to tell us everything we need to answer the question. So for part A, what we could say from here is we could say W of x is increasing. And where is it increasing? It's increasing on the space here from -1/2 to infinity. Okay, it's increasing on -1/2 to infinity. And it's decreasing on the space here from -infinity to -1/2. If I had to throw a justification in, I would say here because, so I'll say because W prime is greater than 0 on that interval, okay? Or I'll say on -1/2 to infinity, okay? And I'm going to say next that W is decreasing on the other interval for the reason that W prime is negative on the other interval. For part B, I could say that W of -1/2 is a local minimum. Okay, so W of -1/2 is a local minimum. And our because is that W prime changes from negative to positive at x equals -1/2. For part C, we could say that W is concave up on the space from -1 to infinity because W double prime is positive there. And then W would be concave down from -infinity to -1 because W double prime is negative on that interval. And now for the last part here, we're looking for the point or points of inflection of W of x. And notice that we do have a sign change. If we look at the sign chart for W double prime, we have a sign change at x equals -1. So we could say W has a point of inflection at x equals -1 because W double prime changes signs there. Question 13, we have f of x equals sine x plus cosine x. And we have to find the 103rd derivative of f of x. So for this one, don't actually find 103 derivatives. We're going to keep taking derivatives until we see a pattern. And then we're going to see where does 103 fit in that pattern. So f prime, the first derivative, we take the derivative of sine and we get cosine. And then we have the derivative of cosine is minus sine. And then for the next derivative, we have f double prime of x equals the derivative of cosine is minus sine. And then we have the derivative of sine is cosine. So we get minus cosine x. Just know when you derive a cosine term, there's a sign change. When you derive a sine term, there is no sign change. So that's how I know how to go from here to here. And now next we have f triple prime of x, the third derivative. We have the derivative of sine is cosine, so we just get minus cosine x. There is no sign change here. But since we're deriving a cosine term, we're going to get a sign change to plus sine x, okay? So that's how we're going from here to here. And now for the fourth derivative, don't go and write 4 primes like this, okay? That just looks not nice, okay? Then we start using this notation over here. We put a parenthesis like this, and then a close parenthesis, and we say the fourth derivative of f of x equals, and now the derivative of cosine is minus sine, so we go from minus cosine back to positive sine, and the derivative of sine is cosine. See how now, by the time we take the fourth derivative, we're back to where we started. So the pattern repeats every 4. So all we have to do here is do 103 divided by 4. And if I do the division, 4 goes into 103 25 times. And I subtract 100, I get a remainder of 3. That remainder of 3 tells me where the 103rd derivative lands in the pattern. It's going to land at this one. Okay, so the remainder corresponds to the prime that we look at. You could think of f of x as having no remainder. Okay, so this is like doing 0 derivatives. Okay, so the zero derivative is just the original function here. So that would happen if we had a remainder of 0. It would bring us right back to f of x. But remainder 3 tells us that the 103rd derivative of our function is equal to our third derivative of f. So this is equal to negative cosine x plus sine x. Question 14, we have f of x equals, and we have this quadratic function here, and the domain is restricted from 1 to infinity, and we need to find the derivative of f inverse at 12. So for this one, we have to know this formula. F inverse prime of x is equal to 1 over f prime of f inverse of x. Okay, this is how you find the derivative of an inverse function. Now, some people might say, well, why don't I just find f inverse explicitly? But with a function like this, it's not going to be pleasant to separate variables. Okay, so for something like this, it's just better that we use the formula. Okay, and they could also design questions where you just have to use the formula. You know, if you want to take this and complete the square and, you know, do your algebra, you know, you could try all that, but it's better, once again, to just use this formula, because if you can get away with not using the formula, they may just design a question where you can't get away with it. So just commit to knowing this formula. So what I could say here, though, is this function here is quadratic, and what they're doing is they are restricting the domain so that we're just looking at this side of the quadratic. The reason why we can't look at the whole thing is then this function would not be 1-to-1, and it would not have an inverse. Okay, so that's why the domain has to be restricted here. Now, we could play a guessing game and see when is the function reaching a height of 12. Or what we could do is we could set 12 equal to the function here. And we have 12 equals x squared minus 2x plus 4. And then we do a little bit of algebra here. We go minus 12 on both sides. And we have 0 equals x squared minus 2x minus 8. And now I could factor. I could say 0 equals, we have x minus 4 times x plus 2. And this gives me two solutions here. I have x equals 4 and I have x equals negative 2. I'm going to reject this one because our domain is x values from 1 to infinity. Okay, so this is the one we're going to use. And what this tells us, it tells us that f of 4 is equal to 12. And why is this useful? Well, if f of 4 is equal to 12, then I could say that f inverse of 12 is equal to 4. Okay, so this is going to be a very important value to use for this question. And then how we use it is to use the formula, we have to know what f prime of x is as well. So I'm going to find now f prime of x. And for this, I just use the power rule. The derivative of x squared is 2x. And then minus the derivative of 2x is 2. The derivative of plus 4 just goes away. So now if I want to find f inverse prime at 12, now I could just plug into the formula. I have f inverse prime at 12 is equal to, and then I have 1 over f prime of, and we have f inverse of, and we're plugging in 12 here. But you see what we found over here, f inverse of 12 is equal to 4. So now I have 1 over f prime of 4. So you see I'm just plugging in here. I'm replacing this piece. I'm replacing f inverse of 12. This piece is equal to 4, and that's going here. Okay, so now next, I just plug in 4 to my derivative. So I have 1 over, and then I have 2 times 4 minus 2. And this is going to simplify to 1 over 8 minus 2 is 1 over 6. So this is our value here for f inverse prime at 12. Question 15, air is escaping a spherical balloon at a rate of 12 cubic centimeters per minute. How fast is the surface area shrinking when the radius is 6 centimeters? So for a question like this, I'm going to write down all of the formulas first. The volume of a sphere is 4/3 pi r cubed. And the surface area is equal to 4 pi r squared. And if you don't know how to go from volume to surface area, a nice way to get from here to here is you could derive this equation with respect to r, and it actually gives you the surface area equation. Okay, so that's just a nice one to know. And for this related rates question, what you should do for this question, and pretty much all related rates questions, is extract the rates. They're telling us that air is escaping. So the air is leaving the balloon at a rate of 12 cubic centimeters per minute. So this tells us the change in volume over time. So we have dV dt is equal to, and I'm going to say negative 12 cubic centimeters per minute. The reason why I'm putting a negative here is because air is leaving the balloon. Okay, so the volume is going to be shrinking. So the rate of change of the volume with respect to time has to be negative. Okay, and they want us to know, or they want us to find here, how fast is surface area shrinking when r equals 6 centimeters. Okay, so at the end, we're going to plug in r equals 6 centimeters, and we want to know what is ds dt at the moment r is equal to 6 centimeters. Okay, this is what we're looking for. So in order to do this, what we could find here is the derivative with respect to time of both of these equations here. So we have d over dt we're doing on both sides. And for the first equation here, we're going to find we have dv dt equals, and then we have 4/3 pi, and the derivative of r to the third with respect to time is going to be 3r squared, but we have to tack on dr dt. Okay, the concept for these questions is we're basically using the chain rule here. And this is very similar to implicit differentiation, that what we're doing is we're deriving, in this case, let's say r to the third with respect to time. So what we're doing is the derivative with respect to r of r to the third, but then multiplying by dr dt. You can see how dr over dr would cancel, bringing us right back. But that's why there's this extra piece at the end. So if you forget those pieces, these questions just basically start to fall apart. So now what we do is we're going to solve for the rate dr dt. Okay, we need to know how fast is the radius changing. In this question here, so if I just draw a balloon off to the side here, we have some balloon and the radius at this moment is 6 centimeters. Okay, so at this moment it's 6 centimeters. And we could see that as the air escapes the balloon, the radius is going to be shrinking and the surface area is going to be shrinking. So the question is how fast? So now in order to solve for this unknown rate here, the dr dt, we want to solve for this. What we could do is we could just plug in everything now. So we have dv over dt is -12, and then we have cubic centimeters per minute. Now, depending on your professor or teacher, some may want to see the substitution with the units here. Others are okay with you just plugging in the numbers and then writing the correct units at the end. But I'll show this one with the substitution with the units. So we have 4/3 pi, and then 3 times the radius that we're plugging in is 6 centimeters, and squaring it, and then we have dr dt. And then from here, 3/3 cancels, and we have -12 cubic centimeters per minute is equal to, and then we're going to have 36 times 4. And if we do 36 times 4, that's going to give us 144. So we're going to have 144 times pi, and we have centimeters squared, so we have square centimeters, and then dr dt like this. So now we'll just make a little bit more space. I'm just going to squeeze these together here. So we'll move these all next to each other like this, our givens, and what we're looking for. So now what I'm going to do is I'm going to divide both sides by 144 pi square centimeters. Okay, so we divide by 144 pi square centimeters. And on this side, everything cancels out except dr dt. Okay, so I'm just going to write that over here. We have dr dt equals, and on this side, square centimeters wipes out, and this becomes centimeters to the first. And we have -12 over 144 makes 1/12, and the pi is going to be on bottom like this. And then we have centimeters per minute, okay, which makes sense because the radius is a one-dimensional measurement, so the rate should work out to something like this. So now the next thing that we're going to do here, I'm just going to transfer this over here. So this equation, we want to know how fast is the surface area changing. So this piece is going to be useful, but now we're going to derive with respect to time. So we derive this one, and we're going to have ds dt equals, and then 2 times 4 pi gives us 8 pi r, but then we tack on dr dt. So now we're ready to find this unknown rate. What is ds dt the moment that r is equal to 6 centimeters? And this is going to give us 8 pi times 6 centimeters. And then dr dt is, we have, I'll write this in red, -1/12 with a pi in the denominator. And then we have the units here are centimeters per minute. Okay, and if we work this out, let's just see here. We have, I'll just do this math off to the side here. We'll just think about it. We have 8 times 6 is 48. So we get 48 pi, and we're dividing by 12 pi. And you see how pi over pi cancels, and 48 divided by 12 is 4. So this works out to, we would have a positive times a negative is negative, and then we're going to be left with a 4 here. Okay, so we have negative 4, and then centimeters times centimeters is square centimeters per minute. So ds dt at r equals 6 centimeters, the rate of change of the surface area is equal to negative 4 square centimeters per minute. And this means that the surface area is shrinking at a rate of 4 square centimeters per minute. Question 16, water is being poured into a cone-shaped paper cup with a radius of 6 centimeters and a height of 18 centimeters at a rate of 9 cubic centimeters per second. The water forms a similar cone inside the cup as it fills. And we have to do two things. Write an equation for the volume of the water in the cup as a function of the water's height, and then we have to find how fast the water level is rising when the water is 12 centimeters deep. So first, let's just draw this out. So we have a paper cup in the shape of a cone, and we're told the dimensions of the cup. So the cup has a radius of 6 and a height of 18. So I'm going to say over here we have a radius of 6 and a height of 18. And we're told that as the water fills the cup, the cone is going to maintain its proportion here. It's going to stay with this ratio of 6 to 18 radius to height. So let's just say if we look at the water level, let's say it's somewhere over here. Then what we're allowed to say in this question is that the ratio of the radius to the height is equal to, so I'm going to say the ratio of the radius to the height is equal to 6 over 18. And now I'm just going to reduce this on the right, divide the top and bottom by 6, and we get r over h equals 1/3. And now I'm going to solve for r, so I'm going to multiply both sides by h, and this tells us that r is equal to 1/3 h. And now this is going to help us answer part A. We have the volume of a cone is 1/3 pi r squared h. So if we want to write an equation for the volume of water as a function of the water's height, then we need this to be all in terms of h, not r and h. So now I just make a substitution. We have 1/3 pi times r is 1/3 h, and it's being squared, so I'm just making a substitution here. And then we do times h at the end. So we have 1/3 times pi, and then 1/3 times 1/3 is 1/9, and we get h squared times h. So our equation here, we're going to have 1/3 times 1/9 is 1/27, pi, and then h squared times h is h to the third. Okay, so this finishes part A, and now for part B, we're going to have to take a derivative with respect to time. So for the next phase of this question, we're going to do the derivative with respect to time on both sides, and the derivative of the left side is going to give us dv over dt. And now for the right side, 1/27 times pi is a constant, so we leave it alone. But now the derivative with respect to time of h to the third, we're going to have 3h squared and then dh dt. Okay, so we're treating this a lot like implicit differentiation. And now we could just simplify here. 3/27 simplifies to 1/9. So we could say that dv over dt is equal to, we have 1/9 times pi, we have h squared, and then dh dt. But now let's go back to the beginning of the question here and extract the givens. We're told that the water is being poured in at a rate of 9 cubic centimeters per second. So that's telling us what dv over dt is. Okay, so I'll just say that over here. We're going to say dv over dt is equal to, and we have 9 cubic centimeters per second. And then the next thing we're looking for in part B is how fast is the water level rising when the water is 12 centimeters deep. Okay, so this is going to be, we're concerned what's going on here at h equals 12 centimeters. Okay, so we're going to say here, part of the givens is h equals 12 centimeters. So we're going to have to plug this in, and we're going to say here that the rate of change of the volume is 9 cubic centimeters per second. So if we want, what we could do first is solve for dh dt, because we're looking for how fast is the water level rising. So this is dh dt. So I'm going to divide both sides by 1/9 pi times h squared. Okay, so divide both sides by 1/9 pi and then h squared. I could plug in and then solve at the end, or I could just solve for dh dt all at once and then just plug in to get our answer. So we have dh dt is equal to, we have dv dt, and we're dividing this by 1/9 pi h squared. So now what is the rate of change of the height when the water is 12 centimeters deep? So that's dh dt when the height is equal to 12, okay? And I'll write the units out here at the end. So dv dt is 9, and we're going to have 9 over, and then we have 1/9 times pi, and then we have h squared, and h is equal to 12, so we're going to have 12 squared like this. So now let's just simplify this. So this part over here, I'm just going to go piece by piece. 9 divided by 1/9, that's going to give us 81. So we're going to have 81 divided by, and we have pi times 144. And then from here, I'm going to divide the top and bottom by 9. So if we divide top and bottom by 9, 81 over 9 is going to give us 9. And 144 divided by 9 is going to give us 16. So now I'll say our answer with the units at the end. So we have dh dt at h equals 12 centimeters is equal to, and we're going to have 9 over 16 pi. And the units here for the height, the rate of change of the height is going to be centimeters per second. Okay, so we're going to have centimeters per second like this. And here's our solution to 16. Question 17, we're going to use the closed interval method to find the absolute maximum and absolute minimum value of f of x on the interval 0 to 3 pi over 2. So when you're looking for the absolute maximum and absolute minimum on a closed interval, what you want to do first is find the critical points. So we're going to find f prime of x, and we're going to have the derivative of 2x is 2, and then the derivative of 4 cosine x is minus 4 sine x. And what we're going to do from here is set the derivative equal to 0 and solve. So we're going to set 2 minus 4 sine x equal to 0. And now we just have to do a little bit of algebra and trig. Okay, so I'm just going to move this stuff over. And from here, we're going to have 2 equals 4 sine x. And then divide both sides by 4. And you've got sine x equals a half. And now from here, you have to know the trig values. So sine of pi over 6 gives us a half. So our first x solution here is going to be pi over 6. But this is a quadrant 1 solution. What we also have to consider is that in quadrant 2, sine is positive. Okay, just remember ASTC. This stands for all students take crack. No, it means all sine, tangent, cosine. So when you have an angle that terminates in quadrant 2, sine is going to be positive for all quadrant 2 angles. So when I have an angle of pi over 6, in quadrant 2, that would be an angle of 5 pi over 6. Okay, the math that I'm doing in my head is this is my reference angle over here in radians. And then what I'm doing is I'm just taking pi minus pi over 6. Okay, instead of going the full pi like this, I use the reference angle and I go pi over 6 radians like this into quadrant 2. So pi minus pi over 6 gives us that second solution, 5 pi over 6. And now from here, we take these values and we throw them in a table along with the endpoints 0 and 3 pi over 2. Okay, so we're going to have 0 is one of the endpoints, then we have pi over 6, then we have 5 pi over 6, and the endpoint here is going to be at 3 pi over 2. Okay, so if we look, we had pi over 6 is over here, this angle. So we have 0, pi over 6, 5 pi over 6, and then we stop at 3 pi over 2. So we're just considering these values here. Now, we plug this back into the original function. So if I plug in 0, I would have 2 times 0 plus 4 cosine 0. And that's going to give me 2 times 0 is 0 plus 4 times 1 is 4. So this would give us our first function value here. For the next value here, we just plug in pi over 6. So we're going to have 2 times pi over 6 plus 4 cosine pi over 6. And for this one, we're going to get pi over 3 plus, and then for this one, we have to know cosine of pi over 6 is radical 3 over 2. So what I'm thinking of for this, I'm just doing 4 times radical 3 over 2, and that's going to give us 2 radical 3 at the end. So we have pi over 3 plus 2 square root 3. And then for the next value here, at 5 pi over 6, we would be in quadrant 2. Okay, notice this is a quadrant 2 angle. So if I plug that into cosine, I'm going to get something negative. So I'm going to have 2 times 5 pi over 6. And then I'm going to have plus 4 times cosine 5 pi over 6. Okay, so this time around, though, I'll just write it here. Is we just, or I just said a moment ago, that this is going to turn into a negative because we're in quadrant 2. So we're going to have minus 4 times square root 3 over 2. And this gives us, after this simplifies here, we're going to have 5 pi over 3, but then minus 2 square root 3. Okay, and for the last value at 3 pi over 2, we're going to have 2 times 3 pi over 2, and then we're going to have plus 4 times cosine at 3 pi over 2 is 0. So this just gives us 3 pi at the end. Now, the mental math here could get a little bit annoying to see which one here is the absolute max or absolute min. Now, one that kind of jumps out right away, though, is 3 times pi. If we say 3 times, let's say, 3.14, like this, that would work out to 9.42, which is obviously more than this value here. So already I'm looking at this and saying like, all right, this is probably the absolute maximum, but there's got to be another way here to be 100% sure that these values are good. So what I'm going to do is I'm also going to consider the first derivative test alongside this. So here's our derivative f prime. Okay, so f prime is here. And what I'm going to do is I'm going to sketch out a graph of f prime. So just imagine that we're writing f prime of x out, but we're writing it as, let's say, negative 4 sine x and then plus 2. So when you're sketching a trig graph like this, what you want to do, and I'll just move this piece down. So I'm going to move this down a little bit like this. We have a midline at y equals 2. Okay, so the midline here, not necessarily drawn to scale, is going to be here. And then our amplitude is going to be 4. So we're going up 1, 2, 3, 4. And we're going down 1, 2, 3, 4. So if the midline is at 2, then the maximum value is going to be at 6. And the minimum value is going to be down here at negative 2. And what we have next, this is just sine x. There's nothing happening on the inside here. So we have a frequency equal to 1, which means the graph is going to complete a full cycle when we get to 2 pi. Okay, so I'm just going to sketch this out here without a calculator just to get a sense of what's going on. So here are the significant points here to consider. And because it's negative 4 sine x, we're going to start on the midline, but instead of going up like this, we're going to go down instead. So we're going to go down here, then we're going to go back to the midline, then we go to the maximum, and then we go back to the midline like this. So now I'm just going to connect all this. So we have these points here connecting to make one full cycle of the sine curve. So here, what we're considering is when is the derivative equal to 0? Notice that we had one here at pi over 6, and our next one was at 5 pi over 6, but those were the only roots between 0 and 3 pi over 2. But the concept of what's happening here is if we look, the derivative is positive on this space from 0 to pi over 6. So the area under f prime is going to tell us the net change of f of x. So this means like starting here, f of x increases, but then f of x, if I highlight this in a different color, decreases from pi over 6 to 5 pi over 6. And then it starts to increase again for the remainder. Okay, so I'll just do this part here in a different color. Notice from 5 pi over 6 to 3 pi over 2, the function is just increasing. Okay, and this area in blue is more than this area in orange. So I know it's going to increase more than it just decreased. So that's why the absolute maximum at the end makes a lot of sense here, because we're increasing, decreasing, but then we're increasing a whole lot more like this. Okay, so the absolute maximum, I'm going to say, is here like this. But now how about the absolute minimum? Okay, so this is the absolute maximum. What about the absolute minimum? Well, notice that the function starts off here at 4. Then it accumulates this much value here in pink, but then it loses this much value in orange. So this graph here is strongly suggesting that the absolute minimum is going to occur here at 5 pi over 6. Okay, so now if we investigate this a little bit more, and let's say we investigate this by just typing these values in a calculator, the values from the calculator are going to support what the graph is saying. So let's say we do the function value at pi over 6. So we have pi over 3 plus 2 square root 3. To 3 decimal places, we get 4.511. And then for the next function value here at 5 pi over 6, if we type in 5 pi over 3 minus 2 square root 3, we get 1 point, and then we get 772 if we round to 3 decimal places. So notice the absolute minimum is here at 5 pi over 6, and that is supporting what the graph of f prime was telling us. We have our sign change here from negative to positive at 5 pi over 6. So we have a local minimum at 5 pi over 6, but using the graph, why is this an absolute minimum? Because the amount of area under the x-axis here in orange is greater than the amount of area here in pink. So even though the function increased from 0 to pi over 6, the amount it decreased from pi over 6 to 5 pi over 6 was greater. So that's why the absolute minimum is occurring here. But typing these values in the calculator supports what the graph is suggesting here. So I'm just going to say that this is our absolute minimum value here. So now we'll just summarize all this here. This is the closed interval method. We'll say that the absolute minimum occurs at 5 pi over 6 and the absolute maximum occurs at 3 pi over 2. Question 18, we have f of x equals square root x, and we're going to write the equation of the tangent line at x equals 100, then use the tangent line to approximate square root of 102. So for this question, what's going on here is we have this function square root x, and this is square root x over here. And our point of tangency is going to be at x equals 100. And if you just think about this, the square root of 100 is 10. So that's going to send us up here. And then we're going to write the equation of a tangent line at this location. Okay, so here's our tangent line. And then not necessarily drawn to scale, we want to approximate 102. So see how 102 is on the curve at about this location, but it's on the tangent line a little bit above. Okay, so our approximation is going to be a little bit over the actual value, but this is the concept of what's happening. So in order to write the equation of this line, I need a point and I need a slope. The point that I'm going with is at x equals 100. So I plug 100 into the function, and that gives us square root of 100 is equal to 10. So this tells us our point of tangency is at 100, 10. And then next, to find the slope of our tangent line, we're going to find the derivative of our function f of x. So f of x is equal to x to the 1/2 power. So f prime of x is equal to 1/2 times x to the 1/2 minus 1 is -half. Okay, I could also write this as 1 over 2 square root x. And now from here, what I'm going to do is I'm going to plug in x equals 100 so we know what is the slope of our tangent line at x equals 100. So f prime of 100 is equal to, we have 1 over 2 times the square root of 100, and that's going to give us 1 over 2 times 10, which is going to give us 1 over 20. So now we write the equation of our tangent line. And the equation of a tangent line, just know you could use this formula, y equals m times x minus x1 and then plus y1, okay? You might recognize this as the point slope form equation, except I solved it for y. So this formula works very nicely for questions like this. So now I'm going to write out our equation. We have y equals, and our slope is equal to 1 over 20. And then we have x minus our x coordinate at our point of tangency is 100, and our y coordinate is going to be 10. So we have x minus 100, and then plus 10 could go on the outside. So now let's use this tangent line to approximate the square root of 102. But notice that square root of 102 is our function evaluated at x equals 102. If I plug in 102 to the function, I get square root of 102. But then using the tangent line, I could say this is approximately equal to, I have 1 over 20, and I'm multiplying by x minus 100, but x we're plugging in 102. And then we have our plus 10 at the end. So now this simplifies to 2 over 20, because you see how I have 100, 2 minus 100 is 2, times 1 over 20 gives me this, and then plus 10. And if I simplify this, now I get 1/10 plus 10. So I could say down here that square root of 102 is roughly equal to 10.1. Okay, so this is going to be our approximation using the tangent line. Question 19, we have f of x is this piecewise function here, and we want to know, is f of x differentiable at x equals 1? And we have to use the limit definition to explain our answer. So let's think about this. We have the formula f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. If this limit exists, then we could say f is differentiable at x equals a. So this is what we want to investigate. Okay, we want to investigate the limit as x approaches, in this case 1. We're going to have a is equal to 1 because they want us to find is f of x differentiable at 1. And if this limit holds true, then we could say, yes, our function is differentiable at x equals 1. But since it's a piecewise function here, what we're going to do is we're going to take the limit as x approaches 1 on the left side and the right side. So the idea behind this question is when we have, let's say, this number line like this, and we're interested in what's happening at 1. When we are on the left side here, so this side is the x less than 1 side, and that's how we approach 1 from the left. Okay, so that's how I think about these questions. This is what's going on in my head when I'm setting up these limits so that I'm setting everything up accurately. Okay, so when we have to find that first limit as x approaches 1 on the left of f of x minus f of 1, the piece that I'm looking at for the left side limit is this one here, because the left side of 1 implies we're talking about x less than 1. Okay, so this is what we're going to have here. We have f of x minus f of 1 over x minus 1. So for this, and for both of these parts here, we're going to find f of 1. F of 1 goes with the equal to part, is going to be negative 1 minus 1, which is negative 2. So now we just go ahead and plug in. We're going to have the limit as x approaches 1 on the left side, and we're replacing f of x with the bottom piece here, the x squared minus 3x. And then we have minus f of 1 is equal to negative 2. So when I get minus 2, this is going to change to plus 2, and we're dividing by x minus 1. And now I just have to simplify that limit. This is equal to the limit as x approaches 1 on the left side, and we have x minus 2 times x minus 1 over x minus 1. And these factors cancel. And when we plug in, we get 1 minus 2 equals negative 1. So this represents our left side limit. Now we will check the right side limit. Okay, so for the right side limit, we are on the x greater than 1 side, and this is when x is approaching 1 from the right. So I'm going to say the limit as x approaches 1 from the right of f of x minus f of 1 over x minus 1 is equal to, and now I'm using this part of the piecewise function, the greater than 1 part. Okay, so we have x approaches 1 on the right, f of x we replace with negative x minus 1, and then we have minus f of negative 1 is negative 2, so this changes to plus 2 like this over x minus 1. So now we just simplify. We're going to get the limit as x approaches 1 on the right side of, here we have negative x plus 1. When we do negative 1 plus 2, it's going to simplify to plus 1 over x minus 1. And now I just have to do a little bit of algebra. So what I'm going to do on top is take out a negative 1 factor, and we have x minus 1 left on the inside. Okay, so x minus 1 on the inside. You could even see if I distribute that negative 1, it brings us right back. And then over x minus 1. And now these factors cancel out nicely, and the limit equals negative 1. But notice what we got here. The right side and left side limits are both equal. The left side limit was equal to negative 1, and the right side limit was equal to negative 1. So this tells us, since these two are equal, that the limit as x approaches 1 is equal to negative 1. So now let's just write that all out. We could say that the limit as x approaches 1 on the left of f of x minus f of 1 over x minus 1 was equal to the limit as x approaches 1 on the right. They were both equal to, let me just clean that up a little bit, make that a little neater. So this was equal to negative 1. So what this implies, this tells us that the limit as x approaches 1 in general of f of x minus f of 1 over x minus 1 is equal to negative 1. So what does this imply? Since that limit exists, this tells us that our function f of x is differentiable at x equals 1. And then we could say f prime of 1 is equal to negative 1. Now, if I want to say one extra thing here, I'm just going to note that f prime of 1 is equal to negative 1. Okay, so this would be the exact value of the derivative for our piecewise function at x equals 1. Question 20, we have h of x equals the cube root of x squared, and we're on the closed interval 0, 1. And we want to find the value c that satisfies the conclusion of the mean value theorem, where state why it does not exist. So for this one, we have to know that in order to use the mean value theorem, we need to show two things are true, or say that two things are true. We need to say that, in this case, h is continuous on the closed interval 0, 1. Okay, so this needs to be true. And we have to be able to say here that h is differentiable. So we'll say h is differentiable, and I'll abbreviate, on the open interval 0, 1. So just glancing at this function here, h of x, if we look, I'm going to say is equal to x to the power over root, to the 2/3 power. This function, the domain, is all real numbers. And the reason for this is we're taking an odd root of x to the second power. So even if this was just cube root of x on the inside, we could take the odd root of positive numbers, 0, and negative numbers. So there's no restriction on the domain. If we had an issue of, like, let's say a square root function, then we have to be a little bit more on the lookout for problems with the domain. But h of x, there's going to be no issues. And if we look at the derivative, so we'll look at h prime next, we have h prime of x equals, and we use the power rule, we have 2/3 times x to the 2/3 minus 1 gives us negative 1/3. And then we could say next that this would be equal to 2/3 times x to the positive 1/3 if I send this down. And then I'll just clean this up once more. I'll say h prime is equal to 2/3 times the cube root of x. So students look at this and they'll say, uh-oh, the domain of h prime is now all x values except 0. And they'll say the second condition is not met because if h prime of 0 is undefined, so they'll say this, h prime of 0 is undefined, this means that h is not differentiable. Okay, so h is not differentiable at x equals 0. And then they'll look at this and say, all right, h is not differentiable at x equals 0, therefore mean value theorem does not apply. But be careful, this is a very dangerous bear trap, okay? The condition here is that our function has to be continuous on the closed interval, but differentiable on the open interval, okay? So the fact that our function is not differentiable at 0 is not a problem. If we look at this function here, just a sketch of this function, x to the 2/3, I like to call this the bird function because if you're not a great artist, it kind of looks like, the bird that you would draw on your paper if you're just drawing birds in the background. But we do have a sharp turn at 0, so our function is not differentiable at 0. But remember, for the mean value theorem, your function has to be differentiable on the open interval. So the fact that we're looking at what's happening from 0 to 1, this is not going to be a problem. So now I'll just get rid of this thought bubble here so we can include this as part of our work. So we're saying here h is continuous on 0, 1, and h is differentiable on open interval 0, 1. So then I'll just say, therefore, the mean value theorem applies. Okay, so the mean value theorem applies to h of x on the interval here 0, 1. So now the way we use the mean value theorem is we just have to set the instantaneous rate of change equal to the average rate of change. Okay, so we're going to set the derivative here equal to the average rate of change of our function on 0, 1. So let me just find the average rate of change over here. So the average rate of change is going to be equal to h of 1 minus h of 0 over 1 minus 0. And the reason why I'm using these function values is because this is the interval that we were given. So this is what I'm finding. And then h of 1 is just equal to 1 to the 2/3 power, which is just equal to 1. And then minus, if I plug in 0 to our function, we get 0 divided by 1 minus 0 equals 1. So this is our average rate of change. But we want to see, this is the mean value theorem formula here. When is h prime equal to the average rate of change? So we're setting these two values here equal to each other. And now we could just go ahead and plug in. So I'm just going to give us a little bit of space. H prime of c, if I plug in c for x, we're going to have 2 over 3 times the cube root of c is equal to, and the average rate of change here worked out to equal 1. So I'm just going to set this all equal to 1. And now for the next part here, I can just do a little bit of algebra. I'll cross multiply, and we're going to have next 2 times 1 is 2, and this equals 3 times the cube root of c times 1. So we just get 3 times the cube root of c. And then from this step, we just divide both sides by 3. And now these terms cancel out. And now we have the cube root of c. I'll just change colors here. So we'll have the cube root of c is equal to, and then we have 2/3. So to get rid of the cube root, I'm just going to raise both sides to the 3rd power. And this tells us that our value of c is equal to 2 to the 3rd power. We have 2 times 2 times 2 is 8. Divided by 3 to the 3rd power gives us 3 times 3 times 3, which is 27. So the value of c that satisfies the conclusion of the mean value theorem is equal to 8 over 27. And a little mental check here. Notice that 8 over 27 is between 0 and 1. So this is really good that we got something that is between 0 and 1. Question 21, we have an optimization question. So we have a rectangle is inscribed under the parabola y equals 4 minus x squared with the base lying along the x-axis. And we want to know what are the dimensions of the rectangle with the maximum area. So I'm just going to sketch this out. So we have the xy axis, and we have the parabola y equals 4 minus x squared, which is going to look something like this. Okay, it's going to open downwards. And the roots are going to be at plus or minus 2. Okay, and this, I'm just doing that math in my head. If I see if I plug in x equals 2, I get 4 minus 2 squared is 0, but it's symmetric here, so we have the same thing happening at negative 2. And a rectangle is being inscribed, which means that the points are going to be on the parabola like this. And our goal is to find the dimensions of the rectangle that has maximum area. So I could have a rectangle like this. I could have one, let's say, up here like this. But the question is, which one, when inscribed, makes the rectangle of maximum area? So what we're going to do is I'm just going to call this point over here x comma y. And I'm going to say this is the rectangle with maximum area. And what we have to be able to do for these types of questions is describe the area or the situation. We have to be able to describe it with a function and then find the maximum or minimum value of that function, depending on if they want us to maximize or minimize. So here I'm looking at this, and how do I get to the point xy? I start at 0, 0, I go over x, and I go up y. Okay, so this rectangle here, this entire thing, we just have to be able to describe the dimensions. So what I'm thinking of for this is I'm thinking this rectangle, the length of the rectangle, see how this distance over here is x, but it's symmetric. So the length is 2x, and the width of the rectangle is equal to y. So I say the area of the rectangle is equal to 2x times y. And it's, once again, symmetric going this way, but the y value, we're only going up like this. That's why it's only a 1y being multiplied. So now this is a equation now with two variables on the right side. We want to turn this into a function of one variable. So this is where we're going to make the substitution. We're going to replace y with 4 minus x squared, because no matter where we are with our inscribed rectangle, the y value is going to be determined by the location of x, and we're going to be on the parabola, so we can make the substitution and say y equals 4 minus x squared. So I'm going to say now that our area function as a function of x is equal to 2x times y is 4 minus x squared. And now I could just simplify this a bit. I could say a of x equals, and we distribute, and we're going to have 8x minus 2x to the third power. So from here, what I could also say is a domain for this. The only domain that makes sense, since I'm focusing here on quadrant 1, our x value is going to be somewhere between 0 and 2. Okay, so that's what I'm looking for our x value. And now to find the value of x that makes everything maximum here, that makes our area as maximum as possible, we're going to take the derivative. So we're going to find a prime, and we get 8 minus 6x to the second power. And now we could set our derivative equal to 0. So we set 8 minus 6x squared equal to 0. Do a little algebra here. I could just add this to the other side. So I get 8 equals 6x squared. Divide both sides by 6. And now I'll write this over here. We get x squared equals 8 over 6, which reduces to 4/3. And now I take the square root of both sides. But notice that I restricted our domain here. We're focusing on the quadrant 1 section here between x is between 0 and 2. So here I could just say x equals, and I just have the square root of 4 over 3. So I'm going to say the square root of 4 over the square root of 3 like this, which gives us x equals 2 over square root 3. Okay, and the reason for this, once again, I'm going from here to here. I'm considering this, and let me just box that off, including the domain like this, like that. The domain is influencing why we're not saying plus or minus. If we said minus 2 over square root 3, that would put us in the quadrant 2 part, but I wanted to make life as nice as possible and put us where all the numbers are positive. But the actual question here is to say what are the dimensions of the rectangle. So for this, we have to say the length and we have to say the width. So for the length, I'm going to say that the length over here is going to be equal to 2 times x. So 2 times 2 over square root 3, which is going to give us 4 over square root 3. And for the width, there's a few different ways we could find it, but that's really just the y value here. And the y value, I could just plug right into the equation from before. So I have 4 minus x squared. And x squared, I could just take this and square it, or I could say, oh, x squared was 8 over 6, which was equal to 4/3. So I could say 4 minus 4/3, which if I turn this into a fraction with a denominator 3, I would have 4 is equal to 12 over 3, and then minus the 4/3 would give us 8/3. Okay, so here is the length and width of our rectangle. Now, before we move on, let's just provide some justification. How do we know that these dimensions here represent the dimensions of the rectangle with maximum area. Well, a of x represents the function that tells us the area of all of these rectangles, where x is some value here between 0 and 2. So if we make a sign chart for a prime, and the sign chart is going to start at 0 and stop at 2 because that's the domain that we are dealing with in this question. And the sign chart is going to tell us why this is definitely the rectangle we want. So we have a critical point at x equals 2 over square root 3. And if I just think about what the graph of a prime looks like over here, the graph of a prime is going to be a parabola. And the parabola opens downward like this because there's a negative in front of the x squared. And if I were to find all of the roots, not just on the space from 0 to 2, we would have two roots at plus or minus 2 over square root 3. So notice that the sign chart would go minus, plus, minus. The graph of a prime is negative, positive, then negative. So from 0 to this root, the sign chart is going to be positive. And then from 2 square root 3 to 2 or even to infinity, the sign chart is going to work out negative. But notice this tells us that a, the function a of x, is increasing and then decreasing like this. So this would count as a local maximum, but it's also going to count as the absolute maximum, because if you think about it, a of x on the space here from 0 to 2 over square root 3 is increasing, and then it's decreasing. So just know this is a very big idea for optimization questions. If you have only one critical point on your domain, and at that critical point you have a local maximum, it's also the absolute maximum. Okay, so this is how we would know that a of 2 over square root 3 is the absolute maximum. Question 22, we need to evaluate this indefinite integral, and we're going to be using this formula. The integral of x to the n power is equal to x to the n plus 1 over n plus 1, and then we tack on plus c at the end. And we can only use this when n is not equal to negative 1. But before we start, remember this phrase, algebra before calculus. Do not just jump into these questions and just try to do the calculus right away. Try to see if there's any algebra you could do first that will clean this up. And in this case, we could do this algebra. We could divide each term by the cube root of x. So we could say x to the third over cube root x, and then we have minus x to the negative 1 divided by the cube root of x. And then we tack on dx at the end. And now from here, we're going to use this rule. We're going to use the rule a to the b over a to the c is equal to a to the b minus c. So if we apply that rule for the first one here, when we do x to the third divided by x to the 1/3, we're just going to combine these to a single exponent. We're going to say x to the 3 minus a third. Okay, and then this becomes 9 over 3. So when we do x to the 9 over 3 minus 1 over 3, we're going to say next that we have the integral of x to the 8/3 power first. Okay, see how we're just doing, once again, x to the 3 minus 1/3, and that gives us this. And then next we'll have minus, and for the next piece here, I'll just write this off to the side. We'll have x to the negative 1 divided by x to the 1/3, and we have x to the negative 1 minus a third. And that would give us negative 3 over 3 minus 1 over 3, giving us x to the negative 4/3 like this. And then we just tack on dx at the end. So now let's apply the power rule. So we're going to have x to the 8/3 plus 1. So we're just taking the power and adding 1. And then we divide by that new power here, plus 1. And then next we have minus. We have x to the negative 4/3 plus 1. And we're dividing by that new power, negative 4/3 plus 1. And we write our plus c at the end. But now here's a little shortcut for this part. If you struggle with fractions, and let's say here adding 1 to a fraction, what I like to do is I just say numerator plus denominator divided by denominator. So I'm just going to do, for this next part here, I'm going to say that this is equal to, so I'll just section this part off, that this is equal to, we would have x to the numerator 8 plus denominator 3 gives me 11 over the old denominator is 3 like this. And then I'm dividing by that same thing. I'm dividing by 11/3. And then I have minus x to the numerator is negative 4 plus denominator 3 gives me negative 1. And then my new denominator is the same as my old denominator like this. And I'm dividing by negative 1/3 like this, and then plus c. All right. If you're just really strong with fractions, then just do, 8 over 3 plus 3 over 3 and just do the fraction math yourself. But now to fully simplify this, what we're going to do is we're just going to say here that this is equal to the reciprocal of 11/3 is 3 over 11, like this. So we have 3 over 11 times x to the 11/3. And then here I have minus, and when I divide by this negative, this is going to change to a plus. The reciprocal of 1 over 3 is 3. And then I have x to the negative 1/3, and then plus c at the end like this. Okay, another nice little shortcut when you're using the power rule is whatever your new power is, the reciprocal goes in front. So if I have a new power of negative 1/3, the reciprocal negative 3 goes in front, but when I have a negative 3 in front, that changes the minus to a plus. So here is our antiderivative for question 22. Question 23, we're going to evaluate this indefinite integral. And for this one, I want to use a U-substitution. So I'm going to let u equal the bottom piece. We have u equals 1 plus secant y. And then once you define u, the next thing you want to do is calculate du. So the middle step here that I skip every single time, unless I'm teaching it to someone for the first time, is I'm finding du dy. Okay, I'm deriving both sides with respect to y in this case. And what we have here is the derivative of 1 is 0. The derivative of secant y is secant y tangent y. If this were an integral in terms of x, then we're basically finding du dx at this step. But then the step from here to the next is to multiply both sides by dy. And this tells us what du is. Du is equal to secant y tangent y and then dy. Okay, so if we follow the steps, we define u, and then we calculate du. So that's why I say we could skip this step. If you could handle doing the times dy all in your head, then you could just go right from the green to the red. And then depending on your algebra strength, from here you can just plug in and solve. But what students will sometimes prefer to do is define u, calculate du, and then they solve for dx. But in this case, we have a dy. So next we could say divide both sides by secant y tangent y. Okay, so we're going to divide both sides by secant y tangent y. And now from here, secant y over secant y cancels, tangent y over tangent y cancels, and we have dy equals, and then we have du over secant y tangent y. And now we're ready to make our substitution. Okay, so we're going to substitute into the integral. We have the integral of secant y tangent y on top over, and now here comes the substitution. So u equals 1 plus secant y. So we put u here, and then dy, we're going to plug in du over secant y tangent y. And the terms here are going to start canceling out. So secant y over secant y cancels. Tangent y over tangent y cancels. So what we have next now is du over u. So for one, the point of u substitution is to take your complicated looking integral and to turn it into something much easier to antiderive. And another thing I want to point out is a step that a lot of students get tripped up at is defining the u term. So I know u is going to be equal to 1 plus secant y because when I derive 1 plus secant y, it gives me the leftover piece. Okay, so see when I derive this, I get secant y tangent y. And if I focus, see how this is what I'm starting with here, the piece I'm deriving gives me the leftovers, secant y tangent y. So that's how I know what term is going to be my u term. I just derive it in my head, and if it gives me the leftovers, then I know that original thing is my u term. And now from here, just be careful. The integral of du over u is technically the integral of u to the negative 1 du, but we cannot use power rule here. Notice that our power, our value n, is equal to negative 1, so we cannot use power rule. We're going to go with, instead, the natural log antiderivative. Just know the derivative of natural log x is 1 over x, so if I antiderive, it brings me back. Okay, so that's how I know here we're going with natural log. The only catch is when we antiderive, we get natural log absolute value of u and then plus c. So then all I have to do here to close this out is say natural log absolute value of u is 1 plus secant y. I close the absolute value, throw on the plus c. Question 24, we have to evaluate this indefinite integral. And for this one, we're going to use a u substitution. But this one's a little trickier. We have to get this in the form of du over u squared plus 1, or 1 plus u squared. So we could say the antiderivative is tangent inverse u and then plus c. Okay, so this is the formula we want to use for this question here. So we're going to have to complete the square. So to complete the square, we're going to have to target the quadratic piece on bottom. So we could rewrite this as the integral of 1 over x squared plus 4x. But now I'm going to look at that coefficient 4, and I'm going to say, okay, half of 4 is 2. So we have half of 4 is 2, and then we have to square it, and it brings us right back to 4. So that's the number that I'm going to add and subtract on bottom. So I'm going to go plus 4 and then minus 4 right after. And then I write the plus 5 at the end. And you'll see why I did this in a moment. Okay, so we have this and then dx at the end. So now when we simplify, I just want to focus on this piece in purple. The x squared plus 4x plus 4, that's a perfect square trinomial, and it's going to factor very nicely. So we're going to have 1 over, and then the stuff in purple is going to factor as x plus 2 squared. So I could write the stuff in purple as x plus 2 squared, and then the rest here, the negative 4 plus 5, I could write as plus 1. And now if we want to see, if I were to expand this, I would get x squared plus 4x plus 4. And then if I do plus 1, that would give me the plus 5, matching exactly what we started with on bottom. And then, of course, we have the dx at the end. So now we're ready to make our u substitution, but our u term is going to be the stuff inside parentheses being squared. So we're going to say next that u is equal to x plus 2. And then du, the derivative of x plus 2 is 1, and then I just tack on dx. So when I make the substitution here now, what I'm going to have next is I'm going to have the integral of 1 over u squared plus 1, and then dx I could just replace with du. And now this is just matching the formula. We're going to have tangent inverse of u, and then plus c, and then I just have to plug in for u. I get tangent inverse of x plus 2, and then I just tack on plus c at the end, and here is our antiderivative. For question 25, we're anti-deriving again, but for this one, I want to point out some really common antiderivatives that show up. When you have e to a constant times x, the antiderivative of e to the kx is 1 over k, e to the kx, and then plus c. But remember, this works when k is a constant. If I have something like the integral of cosine kx, then this anti-derives to 1 over k, sine kx, and then plus c at the end. Okay, so these are just really common antiderivatives, and they involve the term here, x, having a coefficient of k in front where k is constant. If I had it for secant squared, it's the same concept that will apply. That I look at this and say the antiderivative of secant squared is tangent, but I'm going to have 1 over the constant times tangent of the constant times x, and then plus c. So if I apply that concept all the way through, then I'm going to have our constant here, I'll call it our first constant, is equal to 4. Our second constant is equal to 3. And then our third constant is equal to 1/3. So I just apply this formula all the way through, and I get 1 over 4 e to the 4x. And then here I have minus 1 over 3, and then I have sine of 3x. And then last, I'm going to have plus 1 over 1/3. So I get 1 over 1/3, and then tangent of 1/3 x, and then plus c at the end. So now I'll just simplify all of this. We're going to have 1/4 e to the 4x minus 1/3 sine 3x, and then plus 1 over 1/3 becomes 3, and then tangent 1/3 x, and then plus c at the end. Question 26, we're going to use the limit definition of the integral with the right Riemann sum to find the integral from 0 to 2 of x squared dx. And these are the formulas that we need. So for this, we have an a value of 0. So we have an a value of 0. We have a b value equal to 2. These are our limits of integration. And these help us find delta x, which we do b minus a over n. Okay, so delta x is going to be equal to 2 minus 0 over n. Or we could just say 2 over n. So now to use this formula can be a little bit complicated, but my best advice is to just go piece by piece. Okay, it's very heavy with algebra. So when I want to find, let's say this piece over here, the f of a plus k delta x, we're going to have f of a is 0 plus k times delta x is 2 over n. Okay, so now this is going to give us f of, and we have 2k over n. And now if we look at the formula here for the definite integral, f of x is our integrand function. So we could say that f of x in this case is equal to x squared. So when I need to find over here what is f of 2k over n, f of 2k over n, I could say is equal to 2k over n and then squared. And then this gives me 2 squared is 4, k squared is k squared, and n squared is n squared. So this piece is going to be very important. That's the piece in red. So now what we could do is we could set up the expression here with the Riemann sum. So next we'll say the integral from 0 to 2 of x squared dx is equal to the limit as n goes to infinity of, we have the summation going from k equals 1 to n, of f of a plus k delta x. That's this entire piece over here. That was the 4k squared. So just make that neater, 4k squared over n squared. And then we have to multiply by another delta x at the end. See that delta x over here? So I'm just going to put another times 2 over n at the end of the expression like this. And now I could just simplify first before we start expanding. And we're going to have, let's see here, we have 4 times 2 is 8, but then we have n squared times n on bottom is going to give us n to the third. So we could say that this is now equal to the limit as n goes to infinity, and we have the summation going from k equals 1 to n, and we're left with 4 times 2 is 8, k squared over n to the third. But now what I want to do from here is I actually want to expand this out. Okay, so this is the integral from 0 to 2 of x squared dx. So I'm going to expand this series here. I'm going to start at k equals 1. So we start at 1. And then we stop at n. Okay, so this is what's going to happen here. So I'll write that result over here. So now we could say the integral from 0 to 2 of x squared dx is equal to the limit as n goes to infinity of, and now this is the key. For a series like this, what you want to do is you want to treat the value k here. The value k is the variable of the series. Okay, so when I start plugging in, I'm plugging in for the k values. The n value here being raised to the third is going to be left alone. So I could say 8 over n to the third. This piece is not going to be affected by this series when we start expanding this. Okay, so we're just plugging in, starting at k equals 1 and stopping at n. So what we're going to have next, if I just focus over here on this piece, so let's say I have k squared. This part I'm starting at 1. I'm going to have 1 squared plus 2 squared plus 3 squared all the way down to I stop at n squared. Okay, so I'm stopping at n squared. But this was another formula that I gave here. 1 squared plus 2 squared plus all the way down to n squared gives us this expression here. So now I could say that the integral from 0 to 2 of x squared dx is equal to the limit as n goes to infinity of 8 over n to the third times, and now the stuff in pink, I could substitute and write n times n plus 1 times 2n plus 1, and then all of this divided by 6. Okay, so now this will start to simplify. And what we could do from here is to evaluate this limit, we could use that idea from before that we only have to focus on the leading terms since we're finding a limit as n goes to infinity. So I could rewrite this now and say that the integral from 0 to 2 of x squared dx equals the limit as n goes to infinity. And we have 8 over 6, I'll put on the side like this. But now if I were to expand n times n plus 1 times 2n plus 1, the leading term would be n times 2n, which would be 2n to the third. Okay, and then on bottom, we have just that lone n to the third term like this. But remember, limits at infinity, we only have to worry about the leading terms. And now notice that these terms here just cancel out. So this leaves us with, if we reduce, 2 over 6 reduces to a third. So this tells us the integral from 0 to 2 of x squared dx is equal to just 8/3. Okay, so this is using the limit definition of the integral. We could find our definite integral is equal to 8 over 3. Now, just a side note, for a question like this, what I would do is I would use the fundamental theorem of calculus to check my answer. So I would do the antiderivative of x squared is x to the 3 over 3. And then I'm evaluating this from 0 to 2 here. And what we're going to do is we're going to write on the side, I have a 1 in front of my x to the third. So I could say 1/3 on the side. And then I substitute in 2 for x. So I have 2 to the third. And then minus, I plug in 0 for x like this. And notice what this gives us. We would have inside the parentheses here, 2 to the third power is 8. Minus 0 to the third power is 0. And this gives us 8/3, which matches exactly what we have here. Now, of course, this is way faster, but this is a way more conceptual approach to what an integral actually is. But either way, we're getting 8/3. Question 27, we're going to assume f of x is continuous for all real numbers x. And then we have if the integral from 0 to 8 of f of x dx is 10, and the integral from 5 to 8 of f of x dx is 6, what is the integral from 0 to 5 of x plus 2 times f of x dx? So for this one, it helps to know the following integral properties. When you have an integral, let's say you're dealing with a function like f of x, and you're going from, let's say, a to c, and you have a pit stop at b, then what you could say is the area from a to b plus the area from b to c under the curve is equal to the area from a to c. Okay, so in this case here, since our function f is continuous for all real numbers x, that means we don't have any vertical asymptotes or anything happening here that could throw this whole question off. We could say that the integral from 0 to 8, let's say that's the entire space here, is equal to the integral from 0 to 5 of f of x plus the integral from 5 to 8. Okay, so this we are allowed to say because of, properties of definite integrals. Usually we'll say something like, the integral from a to c equals the integral from a to b plus the integral from b to c, something like this, with f of x dx the whole way through. But I'm just applying that property for integrals to this question here. Okay, so now that we have this all set up, we could just go ahead and plug in and find what we need. So the integral from 0 to 8 of f of x dx is equal to 10. So I have 10 equals. And then I have the integral from 0 to 5 of f of x dx plus the integral from 5 to 8 is equal to 6. So then if I want to solve for this piece, I could just go minus 6 on both sides. And this tells me then that 4 is equal to the value of the definite integral from 0 to 5 of f of x dx. So now we're going to use this to answer the question, okay? So I'm just going to box this off because this is going to be a very important piece. So now what I could do with this integral is I could say the integral from 0 to 5 of x dx, and now plus the integral from 0 to 5 of 2 times f of x dx. Okay, so there is another property for integrals. Basically, for indefinite and definite integrals, when you have something like integral f of x plus or minus g of x on the inside, you are allowed to break this up as the integral of f of x plus or minus the integral of g of x. Okay, this is a nice property to use for integrals. Okay, so we're allowed to use this one. We could also take constants outside the integral. So if I have, let's say, integral of c times f of x, I could say this is equal to the constant times integral f of x dx. And this also applies for definite integrals as well. So maybe one more step here. I'll just go ahead and apply that constant property. We have the integral from 0 to 5 of x dx plus 2 times the integral from 0 to 5 of f of x dx. So now for this piece, I'll underline in purple. We're just going to say, to evaluate this, we're going to use the fundamental theorem of calculus. So I'm going to do the antiderivative of x to the first is x to the second, and then divided by 2, but I'm evaluating from 0 to 5. And then we're going to have plus, for the next piece, I'm just using what we had in blue over here. So plus, we're going to have 2 times the integral from 0 to 5 of f of x dx worked out to 4. So now we'll just give ourselves a little space. We're going to say this is equal to, so this is a 1/2 in front of the x squared. I'm going to have 1/2, and then I'm going to have 5 squared minus 0 squared. Okay, so I antiderive, I plug in the upper limit to the antiderivative, the lower limit, and then subtract. And then we're going to have plus 2 times 4 at the end just gives us 8. So now we simplify here. This is going to be equal to, we're going to have 25 over 2 plus 8. And 8 I could just express as 16 over 2. So I could combine these into a single fraction. 25 plus 16 is 41. So I have 41 over 2. Or I could say 20.5, but I'll just stop at this part. Question 28, we're going to evaluate this definite integral using the fundamental theorem of calculus. So first, we're going to do algebra. We're going to rewrite the stuff on the inside in rational exponent form. So we're going to have x to the power 2 over the root 3. And then next we have plus x to the invisible power 1 over the root 5. And then we tack on dx. So now from here, we antiderive first. So we're going to say x to the 2/3 plus 1 is going to give us 5/3. And then we divide by 5/3, which is the same thing as multiplying by the reciprocal 3/5. Okay, that's just a little shortcut that I like to use. Whatever my new power is, I just put the reciprocal in front like this. And then next we have plus, and then we've got x to the 1/5 plus 1 gives us 6/5. The reciprocal of the new power is 5/6, and that goes in front. But now from this part forward, it gets a little tricky with simplifying, okay? So just be very careful here. We plug in 1 first, so we're going to get 3/5 times 1 to the 5/3, and then plus 5/6 times 1 to the 6/5. But the part where most students mess up is going to be this part here, okay? So I'm just going to give a little space, and we're going to break this next part down very, very carefully. Okay, so when we plug in -1, we have to look out for the odd roots, okay? Because the sign change is what's going to throw this whole question off if we miss it. So we're going to have 3/5 times -1 to the 5/3. And then we've got plus 5/6 times -1 to the 6/5. Okay, see, I'm just plugging in -1 for each of these. So when students start this, they're usually fine dealing with, just saying, all right, 3/5 plus 5/6. Because when you raise 1 to any power, you just always get 1. So nothing exciting happens in the blue. But in the red, we just have to be very careful. For one, the parentheses matter a lot. And then the next thing to look out for is notice that we have an odd power here, but this one is even. Okay, this makes the world of difference. The reason being that when I do something like -1 to the 5/3, this is equal to the cube root of -1 to the 5th. So when I have an odd power attached to -1, I'm going to take the cube root of -1, which comes out as -1. But when I have an even power, like in the second case here, something like -1 to the 6/5, I'm going to have the 5th root of -1 to the 6, and that's going to give me the 5th root of +1, which gives me +1. Okay, so this is going to be really, really important for this part here. So this is going to give me, we're going to have 3/5 times -1 to the 5/3 works out to -1. And then we have plus 5/6 times -1 to the 6/5 works out to +1. So now if I just do one more step of simplifying here, we're going to have 3/5 plus 5/6. But then minus, in parentheses, we get -3/5 when we do 3/5 times -1 plus 5/6. So here, when I subtract, the sign is going to distribute, but notice that 5/6 minus 5/6 is going to cancel. We're going to get 3/5 plus 5/6. Minus turns this to a plus. But when I do the minus times, plus 5/6, think of that as doing -1 times 5/6. I get minus 5/6. These terms cancel. And I'm left with 3/5 plus 3/5, which is 6/5. Okay, so for questions like this, it's usually the algebra that throws a lot of people off. You still have to be careful anti-deriving, but just watch out for those sign changes. Question 29, we have the piecewise function h of x below, and we want to find the integral from -3 to 3 of h of x. So for this one, I want to focus on the bottom piece first of this piecewise function, because this is going to be the tricky piece to deal with. So you might recognize this equation here, x squared plus y squared equals 9, as the equation of a circle with radius 3 centered at 0, 0. So when we look at this graph over here, this models the equation above. But now what I want to do is I want to solve this equation for y. So we have y squared equals, I subtract x squared on both sides, and I get 9 minus x squared. And then if I take the square root of both sides, I get y equals plus or minus the square root of 9 minus x squared. Now, the reason why I have to express this as plus or minus is that a circle is not a function of x. It fails the vertical line test. So the plus and minus are very important. The plus would represent the top piece here. This would be the y equals square root 9 minus x squared part. And then underneath, I would have the y equals minus square root piece. Okay, so this would be y equals minus square root of 9 minus x squared. So for this, how does that help us with the question? Well, when we sketch out h of x, so I'm just going to draw h of x over here. Let me just make this a little bit bigger. So we have h of x, and I'll throw it over here, is like this. And for this piece here from 0 to 3, we're just going to be focusing on the top half of the circle, but I'm only going to focus on the quarter circle because we're going from x equals 0 to x equals 3. Okay, so that's how we're going to sketch this piece. And then for the other piece here, the x plus 3, and we're looking at the space here from -3 to 0, that would be the line y equals x plus 3, but I only care about this piece here. Let me just draw that a little neater. I only care about this piece going from x equals -3 to x equals 0. And at x equals 0, we would land at the point 0,3, which would coincide with the quarter circle here, which would go up to the point 0,3. So I can leave it colored in like this. And now what we're finding here is the area under the curve. So notice this area in pink is the area of a right triangle, and in purple we have the area of a quarter circle. Okay, so for this one, we'd have to know the formula for the area of a quarter circle is pi r squared divided by 4. And then for this one here in pink, I would say the area is equal to 1/2 base times height. Okay, so now we are ready to evaluate this definite integral. So we have the integral from -3 to 3 of h of x is equal to, and for this one, the area of the pink triangle is 1/2, the base is 3 units long, and the height is also 3 units long. Okay, just know when you're finding the area of a triangle, you should have a right angle connecting your base and height, and since we're using the x and y axis here, there's a right angle here. And then next I have plus pi times the radius of this quarter circle is 3. Okay, so I have pi times 3 squared, and then I'm dividing by 4. So I will leave this answer unsimplified at the end, but we're going to have 3 times 3 is 9, divided by 2 is going to give us 9/2 plus, and this is going to give us 9 pi over 4. So here is our solution to question 29. And now question 30, our last question. So we're going to evaluate this definite integral, and we're going to use U-substitution here. So our U term is going to be natural log x. So we have U equals ln x, and now we calculate du. So du is equal to 1 over x dx. Now from here, if we want, we could solve for dx. So I can multiply both sides by x, and that gives us x du equals dx. Okay, so these two pieces are very important. But when you are doing a U substitution for a definite integral, what you could do over here is you could find new limits in terms of u. Okay, so I'm going to have u equals natural log of my old limit, my old upper limit is e to the pi over 4. Okay, and then here I say, all right, natural log and e are opposites, they just cancel, and this gives us pi over 4, okay, because they're opposites. And then next I would have u equals, my new lower limit is going to be natural log, so I would have natural log of my old lower limit, the x value here is 1, and natural log of 1 is 0. Okay, so just know in general, this is really saying x equals e to the pi over 4 and x equals 1. But when you're writing out a definite integral, you don't say x equals like this if your integral is all in terms of x. Okay, but that's why I'm plugging in for x in my definition for u here. So now that I have all this, I'm ready to transform the integral. So I could say now my new integral is going from not 1 to e to the pi over 4. It's going to go from 0 to pi over 4. And I'm going to have on the inside cosine of u over x, and then dx is equal to x du. And then see how x over x cancels nicely? So our new integral, and I'll write that over here so we have the space. Our new integral is going to be the integral from 0 to pi over 4, and we have cosine u du. So now this is much simpler to deal with. So from here, we just use the fundamental theorem of calculus. We do the antiderivative of cosine u, which is sine u, and then we're evaluating from these new limits from 0 to pi over 4. Okay, what's nice about finding new limits is you're able to just evaluate your new integral, and you don't have to switch back in terms of x. If you decide to switch back in terms of x at the end, like let's say you skip this step, you would have to say, so this is just a side note, okay, I'll just put it in as a thought, is my integral would have to say, let's say cosine u du, and let's say I want to keep my old limits, then I'd have to say from x equals 1 to x equals e to the pi over 4. So if you decide not to find new limits, then you have to specify that these are x limits, and then at the end, you'd have to plug in u equals ln x, and then make your substitution. Okay, but that's why I like finding new limits, is because now I could just solve this out. So now I'm going to have sine of the upper limit, pi over 4, minus sine of the lower limit, 0. And we simplify, we get square root of 2 over 2 for sine pi over 4, minus sine of 0 is 0, so our final answer is square root 2 over 2.